Hi everyone, thanks for coming. We have the pleasure today to have Ofir Press. He's a PhD student at UW, and he's going to talk about a recent work that just got accepted to ACL. So, go ahead.
Thanks. So I also work at Facebook, and I wrote this paper with Noah, my advisor at UW, and Mike, who's my colleague at Facebook. Yeah, there's a few people here, so you can ask me questions. There's also people on YouTube, and I have like the YouTube comments opened up. So if you have a question on YouTube, you can also ask me and I'll answer. I'm gonna try and go through this kind of quickly, so I'll have a lot of time for questions. Let's start. So this presentation is gonna have three parts. We're gonna talk about the Shortformer paper, and we're first going to talk about this observation that we discovered about language models, which is probably true for every single transformer language model and kind of surprising. And then I'm going to present two methods on how to make language models faster, more efficient, and better. Okay, so we're going to start from observation. And to talk about the observation, I have to give a brief overview of language modeling. So when we have a language model, we have a sequence of words, which we feed into the LM, and the LM spits out a probability, right, for the next word. Everybody knows this. So in this specific example, we have 4 input words. And we're going to start. When we design a language model, we have to kind of set the maximum number of input words that the language model can read in at once, right? So for example, in GPT-3, this was 2048. In the baseline that we used for this paper, it was 3000. So there's always some number you have to pick, which represents the maximum number of words that the language model can look at once. And throughout this presentation, I'll refer to that number as L. So the first question that you might have is, what happens when L is increased? This is a question that everybody in the community has kind of been thinking about, I think, and trying to explore. And I think the general consensus is that when we increase L, the performance of the language model increases, right? As we look at more words, performance improves. And at first, this seems to be correct. So what we did here is we trained 8 different language models on different input sequence lengths. So one of these language models was trained on 32 input tokens, right? Some of them were trained on 1,500 or more. So we have different input lengths, and what we see here, so we trained them on Wikitext 103, and then we ran them each on the validation set. And what we see is that the more tokens that your language model can read at once, the better your validation perplexity is. So yeah, that kind of affirms the community's belief. But what we're going to see is that this isn't necessarily true always. And to show that, I'm going to have to first define a few terms which we talk about in the paper. The first of which is non-overlapping training. So non-overlapping training is not anything new. We just assign this name to something that basically everybody in the community already does. So usually when you train a language model, you have a very big input sequence of tokens, and it might be 1 billion tokens long, but your language model has a very limited input sequence length, right? It's 2,000 or 3,000. It's never going to be enough. So you have to take your training set and divide it up into a bunch of different segments, right? And then you train on each one of these smaller subsequences independently. But obviously, like usually the training set is 100 million or 1 billion or tens of billions of tokens. So there's much more than just 3 training iterations, but this is just a visualization of what we do during non-overlapping training. And we also do this during inference, right? When we have a really large inference set, we look at every subsequence independently. And here's a problem with that. If we have this toy example where our entire, say, evaluation sequence is 8 tokens long, and we have a toy language model whose input subsequence length is 4, and we want to evaluate this toy example with our toy language model, we're going to bump into a problem because in the first iteration, so we have to divide this sentence into 2 chunks, right? In the first chunk, everything's going to be okay. But then the second chunk, we notice the problem. So now we're trying to predict the last 4 tokens. And when we do that, when we try to predict the first one of these, of the second chunk, the first token, it can only look at one previous word. So we've previously evaluated this entire subsequence, and now we're evaluating the continuation of the subsequence, but we can only look at one previous word. We don't have any of this. This is obviously going to be really bad for our prediction accuracy because we can't look at a lot of the historical context. And one way to solve this, which was previously proposed, is sliding window inference. And in sliding window inference, so again, we have this long evaluation set represented by these short lines. And so we first take our language model and we evaluate the first subsequence, but then we just slowly slide it 1 token to the right and run the evaluation again. And then we slide it 1 token to the right again, and so on until we finish the entire validation sequence.
Ofir, can I have a question on the previous slide?
Of course, yeah.
So when you evaluate language models, so for example, if you do it on perplexity, the number itself doesn't mean too much, right? You want to compare it to something else. So for example, another model.
Yeah. Exactly.
And you want the comparison to be fair, so they should have the same setup, right? So in the previous slide, when you cut the context in some point, and then it's really hard to predict whatever you want to predict in the second half of the sentence. So it's true that the model would be penalized and it would be hard to predict whatever word it is, but then also all the other models would be evaluated under the same circumstances.
Yeah.
So why is it a problem when you compare?
Yeah, you're totally right. And it's not a problem if you're comparing models that have the same input length, but the problem occurs when you're comparing different models that have different input lengths. So in this slide, we compared, this is what I wanted. In this slide, we compared models that have different input lengths, and that's when the unfairness occurs because these different models divide the evaluation set differently. And so, yeah, I'm going to talk about this in detail in just a second. But yeah, you're totally right. If you're comparing models that are of the same input length, then it's much less of a problem. Where were we? Yeah, so sliding window inference. So yeah, that kind of seems like a better evaluation method because now our first inference step is going to look just like it did before, but now in our second inference step, we're just sliding our model 1 token to the right. And so now when we're predicting the word big, we have all this context to look at. And so now what we're going to do is we're going to take our 8 different models trained on different input sequence lengths, and we're going to use sliding window evaluation to evaluate all of them. And we notice 2 things. So first of all, obviously all the numbers get better. But second of all, and you can see these exact numbers in the paper, it's not super clear here, but I'll tell you that in the non-overlapping case, there's a significant difference between the model whose input length is 3,000 and all the other models. Like the 3,000 model is really, really good. But if you do sliding window inference, then the model whose input length is 3,000 actually performs just as well as the model whose input length is 1,000. And I think that's probably the most interesting observation, or probably the most interesting contribution of this entire paper. The reviewers didn't care about this at all, but they're wrong. Like, this is really, really interesting. The community has kind of been pushing towards longer, and I think everybody thinks that longer is better. But what we're showing here is that if you use a sliding window evaluation method, the model that looks at less at 1,000 tokens can perform just as well as the model that looks at 3,000 tokens.
Well, but theoretically it is better, right? It just depends on, like, maybe it's just that this model is not capable of looking so much in the past that it cannot use it, or that maybe just the text, the sequences are not hard enough that or challenging enough that the model can take this into account.
Yeah, you're totally right. I think a problem that this might be showing is that attention just doesn't really work on very long sequences. This model should be doing much better. So this data set is Wikitext 103. I should have mentioned this. It's 30,000 Wikipedia articles, and the average length of each article there is 3.5 thousand tokens. So the longer model should definitely be doing better because it has more context and it's trying to predict these very long context sequences. But I think what this is showing is that attention kind of breaks down at some point. It's going to be different throughout the paper, but I'm going to be showing a few different models. And it seems like at some point, whether it's 500 or 1,000, attention just kind of stops working. And so, yeah, I think before we think about sequences of size 5,000 or 10,000 or 100,000, we have to try and understand how we can make attention work better for sequences of size 1,500 or 2,000, because it's not really working great.
So just
yeah, sure.
Another comment. So I think it's interesting to maybe analyze the actual texts in this data set and see if the long context can actually contribute to predicting the sequences, like the words towards the end.
Yeah.
Because I can see cases where it is relevant, but also cases where it's not really relevant.
Yeah, that's also right. But this result also occurs. We trained this on the Toronto book corpus. Yeah, you're totally right. It might just not be super useful, but I think these two data sets do have a lot of long sequence dependencies. I think it should be helpful, and it just isn't. Yeah. But yeah, there's lots of questions that could be answered. I can't remember what I'm asking here. Why what? Oh, so why do we think sliding window inference helps so much? I mean, I think it's pretty obvious, but we talk about this a bit in the paper. We call this thing the early token curse. So if you have two different language models, and one of them has 2,000 as inputs of size 2,000, the other has inputs of size 500, and you have this evaluation set that you want to evaluate with each one of these language models, and then this really obvious thing occurs where the bigger language model has much more context for each one of its predictions than the smaller context language model. Because the smaller language model has to kind of start over every 500 tokens. So what I'm going to do here is I'm going to color in red every prediction that has 256 tokens or less of context when you make it. And so what we see here is that in the larger model, there's only 12% of predictions, right, have less than 256 tokens of context. But in the larger model, obviously, 50% of predictions are made with very little context. And so our argument here is that sliding window inference is a fair comparison between different models because it lets every model have as much context as possible for each prediction. And so one of the reasons why in this chart here, these models do so bad, and the difference between the 1,000 and the 3,000 here is really significant. And it might not be because this model is actually weaker. It's just because it's getting less context for each of its predictions. So when you slide this window across, it's just a much fairer and better comparison.
Ofir, another question. Why can't you
Yes.
use the same window for all models?
Yeah, that's a good question. So theoretically, when you train a transformer and you set the input length as 500, if you use sinusoidal position embeddings, you should be able to train on 500 and then do inference on 1,000 or 2,000 or 10,000 tokens. There's nothing theoretically in the transformer models that limits your input lengths during inference just because they were limited during training. But in practice, you can go and try this, and it just spectacularly fails. So if you train on 500 tokens and you give your model 510 tokens during inference, it's going to perform really, really badly. I think that's also an interesting question. You could probably write an entire paper about that. But, and in fact, I am writing an entire paper just about that. Basically, I think that transformers learn specific things about specific positions. And so if they're trained on positions 1 to 500, and they suddenly see position 503 in inference, they kind of get confused and don't know what to do with it. So while theoretically you're right, and we should be able to evaluate all these different models on the same inputs, in practice it just never works out. Are there any other questions?
Yeah, Ofir, you said that attention doesn't really work. What did you mean by that?
We just see this graph here that I should probably move because I keep referring to it. But this graph here where we're making our sequences longer, but performance doesn't actually increase. Oh, actually, it's not this graph. It's this line here. It's the sliding window line here. So we're giving every model the maximal context for each of its predictions. But what we see here is that there's no difference between the result for the model whose input length is 1,000 and the model whose input length is 3,000, even though this model should be performing much better. These are like Wikipedia articles. They're really long sequences. There's probably lots of dependencies in these sequences because Wikipedia usually starts with like a summary of what you're going to see and then like the actual content. And so you keep on kind of referring to the start. Like there should be like some really long-term dependencies that this model should be exploiting. But what we see is that in practice we can achieve the same performance with a model that gets much less inputs. And so what I think is happening is that attention just doesn't really understand how to handle more than 1,000 tokens, and it just doesn't make use of this extra information that it's getting.
So the non-overlapping case improves because of the longer context?
No,
minimum context?
The non-overlapping case improves, yes, because of the what we call the early token curse. In the non-overlapping case, this model is performing much better, not because it's actually better at modeling, but because for most of its predictions, it just has much more context. Think about this model. Every 500 tokens, you're starting it from scratch. And so it just has much less, if you were to do like, average number of context tokens for each one of these models, this would just have much more context. And so this isn't even like an NLP observation. It's just like a math thing. Like this model just has much more context for each of its predictions. And that's why it performs better. It's not actually better at modeling. That's what the sliding window result shows. Because in sliding windows, we achieve the same result here. Okay.
Ofir, I have another question.
Yes.
No, go for it. Do you know if that perplexity gain come especially from the like the tokens at the end of the sequence? Because you're kind of hinting about it, but I'm wondering if that's the case. Did you understand the question? So like
No, I
the,
don't think it is.
so in the graph that you show the performance, the perplexity performances across different L size. So you see a performance gain in the bigger side, right?
Yeah.
So do you know if this perplexity gain comes from actually using this kind of long dependency ranges? So
yeah.
the models are better on the on the words towards the end of the sequence?
Yeah. I mean, if that's not happening, then how else could the performance? Oh, you're saying the performance could improve at the beginning for some reason. I mean, I think that what you're saying is right. I haven't empirically shown it, but I just don't really see the other option being valid.
Like it could happen. Just
I mean, yeah, it could happen, but I don't think it is. But yeah, you're right. I mean, I should go and like empirically look at the numbers. By the way, Anaya, are you looking at the chat? Because I see there's a few things, but I can't really see.
Yeah, I'm looking something. So Gregory asked already, and I see that there's another question from Bishal. Do you want to ask yourself, Bishal?
Hey, yeah, sure. So yeah, my question is regarding the early token curse slide. So even for the sliding window evaluation, the same fraction of tokens should have 256 or less context size, right? The stats doesn't change if we go from non-overlapping to sliding window.
Wait, can you, I didn't get that. Can you ask it again?
No, so like when we are sliding the window for evaluation,
yeah.
So the fraction of tokens that gets 256 or less context size still remains the same, right? So
oh, no, that's no, it's not true. When we do the sliding window, every token has the max. So we're sliding the window by one token each time. So now every prediction has the maximal context that you could ever give it, right? So, so this is the non-overlapping case. So we have this toy sentence and we're splitting it into two. So in the non-overlapping case, this prediction here, big, only has one token of previous context. But if we now slide the window, so cat said on the is our first prediction, and now we're going to just predict. So this is our first input sequence. And then now we're trying to predict this next word here, but we're giving it all the previous tokens. Not all, but almost all.
So it's like we are sliding, but only for the evaluation of the final token in that context window.
Yeah, for every token in our evaluation set, except for the first two, but for almost every token evaluation set, we run the entire language model just for that token.
Right. Okay, got it.
Yeah.
Thanks.
Yeah, we can do more questions about this because I really think that this is super important and everything else doesn't matter. So yeah, are there any other questions? I'll even check YouTube. Let's see if anybody. Oh, somebody asked something on YouTube. Was I able to reproduce this finding in different data sets as well? Yes, in the paper. Oh, so this isn't our archive yet, but in our camera ready, you're going to see almost all of these experiments. We also ran them on the Toronto book corpus, which is a huge corpus of books. And all of these results transferred to that corpus as well. So the answer is yes. Are there any final questions? You can also ask me questions on YouTube. Okay, I think we can move on. So now we're going to talk about two methods that improve training. I think both of them improve the speed of the models, and they both lead to better performance, and both of them keep with the theme of this entire paper, which is that longer isn't always better. And so I'm first going to talk about this stage training method, and here it is. So one thing that short models are really great at is speed, right? So what I did here was I graphed training speed, so tokens per second, for the 8 different models. And obviously, as you go down in input length, your model becomes faster. It stops becoming faster at 128 because at that point, attention isn't the bottleneck anymore. And the bottleneck is actually the feed forward sublayers, and they don't become faster when your inputs are shorter. So there's a limit to this, but shorter is much faster. And so the kind of obvious question to ask is, what would happen if we do the following thing? Let's train on short sequences first, and then take that model and continue doing training for a bit more on longer ones. And that's our method. We call it stage training. And we're definitely not the inventors of this method. Bert already did it a few years ago. And I recently discovered that people are now doing this in vision as well for vision transformers. So it's definitely something that other people have already proposed. But in this paper, we're going to conduct a thorough investigation of this method and why it works, and like a lot of different hyperparams. So if you look at the last part of the Bird paper, they'll tell you that the way they used stage training was they trained their model on inputs of size 128 for the first 90%, and they did the rest of training on inputs of size 512. But Bird didn't really talk about why they used a specific 90-10 split, and they didn't talk about why they went from 128 to 512. Like, did they try any other sequence lengths? And what are the general characteristics of this method? So that's what we're going to do here. And this entire thing is just going to be one slide, basically, but it's like a slide with lots of information. So I'm going to just slowly introduce what we're going to see here. So I've hidden this main part here, and I'm just going to talk about the X and Y axes. So on this axis, we have the initial stage subsequence length. So in all of our experiments, we're going to always have two stages. The first is going to be a shorter subsequence length. And then our second stage is always going to be with inputs of size 3000, because our baseline model that we're comparing to has inputs of size 3000. And so second stage is always 3000. First stage is going to be either 32, 64, 128, or whatever he's here. And then the other parameter that we're going to explore is the initial stage, the number of epochs in the initial stage. So our baseline was trained for 205 epochs. So we're going to train all our models for the same 205 epochs. But we're going to vary the amount of epochs we spend on the first stage. And that's it. So we're only exploring two hyperparams here. And these are the results. So our baseline model achieves 18.6 perplexity. And remember, perplexity lower is better. And our best model here achieves 17.5, which is many standard deviations better than the baseline. But what's interesting is that, oh, do I have flux on? That's not good. But all the highlighted cells here are cells that beat the baseline performance, right? So almost all of our experiments beat baseline performance, which is pretty cool. It shows that this method is really, really robust to hyperparameter choice. And what's cooler here is that all of these methods take less time to train than the baseline model, right? If you're training for 100 epochs on sequences of size 128, and then you do the rest of training 105 epochs on sequences of size 3000, you're definitely going to be much, much faster than a model that spent 205 epochs of training on sequences of size 3000, right? So no matter what you do, almost, you get a model that's better and faster. So yeah, it's just a super cool result. I'm not going to talk much about this next slide, but another thing we can do is just try to match baseline performance with each one of these models. And what we see here is that this model here that was trained on sequences of 128 for 125 epochs matched baseline performance in 37% of the time that it takes to train the baseline. So instead of training on 3000 tokens for 200 epochs, we trained this model on sequences of size 128 for 125 epochs, and then we did another 10 epochs of training in sequences of size 3000, and we matched baseline performance in 37% of the time it takes to train the baseline. Yes, that's it for this part. Let's do questions. He asked, what's the baseline performance? 18.6. The best one in state training was 17.3. No, this is the best one, 17.5 too. Do we have YouTube questions? No.
No, we can move on.
What did you say, Anai?
I don't see any more questions, so we
Yeah.
can move on.
Okay, let's move on. Okay, this is the final part of this presentation, and I'm going to talk about this other method that we introduced called position-diffuse attention, which also goes along with caching. Yeah, let's talk about it. So we're kind of going back now to part one, where our kind of big summary was that we want every prediction to have as much context as possible. And what we saw in part one was that sliding window can do this, and it works great. But what I didn't really mention in part one is that sliding window inference is very, very expensive, right? If you have to, in kind of non-overlapping inference, you're sliding the window by like 1,000 tokens every time if your model is of size 1,000. If you're doing sliding window inference, you're now sliding the model by 1 token every time, right? You're only evaluating 1 new token every feed forward pass. And so it's going to be 1,000 times more expensive or slower. But we can do that during inference because inference is pretty fast. But we'd like to kind of also do this during training. But if training would take 1,000 times longer, that would basically be unfeasible. These models that I showed take about 3 days to train on 8 GPUs, which is already very, very expensive. And not many organizations in the community can run those models. But if you multiply that by 1,000, it's going to be basically impossible. And so in this part, what we're going to try to do is we're going to try to achieve that same result of having more context, but we're going to try and do it in a very quick way. In order to show you what we did, I kind of have to introduce this notation, which is kind of similar to the stuff I was showing in part one, but maybe a bit nicer. So what I have here is a language model whose input length is 3. And I'm just showing you the 2 layers. And I'm showing you where every time step is attending to. And what I'm showing you is the first 2 iterations of training. So in the first iteration, we look at the first 3 tokens, right? And then we look at the next 3 tokens, because we're doing non-overlapping training. And today when we train, of course, whatever we look at in sequence 2 can't attend to the stuff we looked at subsequence during evaluation of subsequence 1, right? What we want is we'd like from every sequence I to be able to attend to the representations of sequence I minus 1, right? Let's say we're language modeling the Wikipedia page for Barack Obama. We're training. When we're training on the second part of the Wikipedia page for Barack Obama, it would be really cool if we could attend to representations we computed at when we were evaluating the previous part of that Barack Obama article. There's one more bit of notation I have to introduce, and that's these letters and numbers. So the letters are going to be the tokens. So it's a continuous sequence of tokens. So it's going to be the alphabet. And then the numbers are going to be the position embeddings that we use. So now when we're training, we take the first subsequence and we give it position embeddings 1 to 3. And then we take the second subsequence. It's a new subsequence, but we're still using the same position embeddings. And so now, remember, our goal is to be able to attend to previously computed representations while we're working on the next subsequence. And so this is kind of the first thing that you try is to just, so, you know, in the first training iteration, you just have the first subsequence, you have nothing else to look back on. But in the second training iteration, we're now just going to add, we're going to attend to not only the new tokens that we're modeling, but we're also going to look back at the previous tokens that we computed, right? That's the kind of basic solution that you'd first try. And you can program this and it absolutely doesn't work. And I think the reason is pretty obvious, right? You're using every position embedding twice. And so the model is probably going to be incredibly confused about the actual ordering of the tokens. because you're using every position twice. It just doesn't make much sense. So this doesn't work. So here's solution number 2. So our first, it's going to be the incrementing solution. So our first iteration is going to look just like always. And then in the second iteration, we're going to increment our position embedding. So now we're trying to model D, E, and F and make predictions here. And we're going to attend to A, B, and C. And now there's not going to be any positional confusion because we gave these new tokens, new positions. And then the third iteration, of course, we'll take the next part of this sequence and we'll increment the positions again. So you can also program this and run this, and this is absolutely not going to work again. And you could probably write an entire paper into why this doesn't work. My intuition is that, again, language models like learning specific things about specific position embeddings. And if you do this thing where you're constantly incrementing the position embeddings, it's just never going to see the same position embedding more than once during an epoch. And it just confuses the language model, and it just doesn't learn well.
But in the third figure, why
Yes.
don't we start from 1 again?
Oh, okay, that's a great question. So Yanai is saying, let's cache D, E, and F and put them over here, and let's assign position embeddings 1, 2, and 3 to them, and then use 4, 5, and 6 again. The problem with that is that transformer models kind of combine for every representation content information and positional information. At the bottom part of the transformer, you add the content embedding to the positional embedding, and you feed that into the transformer. And so throughout the entire transformer stack, every one of your outputs, it doesn't only represent cat or dog or whatever the word is. It also represents a position that word had. So you just can't do what you propose. It's a great question. We're going to talk a lot more about this, but it's just unfeasible in the regular transformer because these D, E, and F tokens, they don't only represent the content here, but they've also been injected with this positional knowledge. And you can't just cache it and somehow change the positions because the positions are part of the representation.
So is this the reason you said it doesn't work, or was it something else?
Oh, no. So what I'm proposing here is much simpler. What I'm proposing here is that you cache these representations.
I got that. Like, I asked if you think that this is the reason that it doesn't work in this way, or is it something else?
What do you mean by I don't understand?
You said that this doesn't really work. So
right.
So I'm asking if this is the reason, because now every time, like, you're kind of starting from the middle and you don't have, for example, the first position embedding encoded anywhere.
Oh, no. I don't think that's why it doesn't work. I think the reason this specific, and I mean, this is all intuition, right? I haven't proven any of this. You could probably write a paper about why this doesn't work. But my intuition is that the language model likes seeing the same position embeddings over and over. And if you have a training set of size 1 billion, it means it's going to see 1 billion different position embeddings. And my intuition is that it doesn't like that. It likes seeing the same position embeddings over and over, and it doesn't like seeing 1 billion different position embeddings. I think it learns specific things about specific position embeddings. And so just seeing 1 billion different ones really hurts performance. So here's our solution. And it's actually basically what Yanai proposed. We found a way to implement what Yanai proposed in a simple manner. And so to implement our solution, we're going to have to find a way to separate the positional information of each representation from the content information of each representation. And so I'll talk about how we do that in a second, but before I talk about that, I'll show you how our solution looks like from like a high level overview. It's basically what Yanai proposed. So in the first iteration, it looks like it always does. Second iteration is like this incremental thing. And then we're going to cache D, E, and F. We're going to change their positions to 1, 2, and 3. And then give the new subsequence positions 4, 5, and 6. So we're always going to cache the representations that we just computed, give them position embeddings 1, 2, and 3, and then take the new subsequence and attend to them. And so this is definitely impossible in the normal transformer, but the community has already shown that you can do this with Transformer XL. So Transformer XL does exactly this, but they do this with something called relative positional embeddings, which are incredibly slow, and they require extra parameters and memory. And so our novelty here is that we show a method to do this that doesn't require any extra parameters or memory, and it doesn't slow down the model at all. We call it position-fused attention, and it's really, really simple. It's basically a line of code. And so to explain it, I have the famous transformer diagram here, and we're doing language modeling, so it's only a decoder. And I'm actually only going to talk about the bottom part that we've already discussed. At the bottom of the transformer, you always take your input word embeddings and you add positional information to them. And so in our model, we're just not going to do this positional encoding part. We're only going to feed into the transformer word embeddings. And the only other thing we're going to change in the model is the self-attention mechanism. And we're actually not going to change the self-attention at all. We're just going to, oopsie, I should talk about this side first. We're not going to change the self-attention mechanism at all. We're just going to change the way that we call the self-attention function. So typically, when you have a self-attention function, you have your keys, queries, and values, right? And they're all the same sequence. And so in our positional infused attention models, we're going to still give the values the same thing we always gave them, but we're going to slightly change how we what we assign to the key and query parameter. We're just going to add position embeddings to the keys and queries. And that's it. That's the entire model. So we don't add position embeddings at the bottom of the network. We just add them before every self-attention call. And we just add them to the keys and queries, not to the values. And what this does is that it means that throughout the entire transformer stack, outputs never have any positioning information, because the output of a self-attention sublayer is a weighted sum of the values. And our values never have any positioning information. So throughout the network, the outputs, the representations of each time step never have any positioning information. And that enables us to do this thing where we take these representations that we computed at training iteration 2, we cache them, and then we can assign new positions to them, because the positions are something that we kind of assign during each feed forward pass, and not something that is saved inherently in each representation. So are there any questions about this? Okay. That's basically it. I'm going to talk about results now for a bit, but we basically covered the entire method. Anyways, so what we did here was we trained these models with positional infused attention and caching with different subsequence links. And what we saw is that performance improved as we increased input size, but then after 500, it started decreasing. And so again, we return to the theme of this paper that for transformer language modeling, longer isn't always better, which I think is really interesting. I'm not going to talk too much about these numbers because you can just see them in the paper. I don't really have too much to say, but of course we beat the baseline and we're super quick. We're just like a smidge slower than the baseline. And we can combine these two methods that I showed you to achieve even better performance. So if you just use caching and position infused attention, you beat the baseline. But if you train that model with state training, it beats the baseline even more. We get good results, blah, blah, blah. That's it. Thank you for listening. Our code and model are on GitHub, and we can do lots of questions now. Yes.
Cool, thanks. If someone has a question, Chester?
Oh, I don't have a question. I was just clapping.
Ah, okay.
Do we have any YouTube questions?
So how do you think to make models better in looking farther away? Or maybe it's not a good direction? Like, what do you think about it?
What do you mean?
Like, should we look for models that can look farther away and improve?
Oh, I mean,
or like, maybe another view on that. Do you think that we should kind of evaluate the models on this kind of graph and say that if there's no constant improvement with longer sequences, maybe there's something wrong with the model or not optimal?
yeah, I don't think, I just think that we need to focus on improving attention for sequences longer than 1,000 words, but shorter than like 2,000 or 3,000. At some point, it seemed like everybody was going for like, 10,000, 20,000, but it seems like there's lots of work to be done in the 1,000 to 3,000 range. It's kind of clear that those models don't really perform much better than models that look at 1,000 tokens, even though they probably should. And so I think it's really interesting to just, instead of try and improve these models by looking at more tokens, to just try and improve existing models. I think there might be some issues with the attention mechanism that we should solve before we try to work on much longer sequences. Yeah. Gil asks, do you have any insight as to why the state training method improves results? Yeah, I don't have much empirical, I don't have much more empirical information that I didn't share here, but I think that my intuition is that attention kind of might be confused by having huge inputs at first, and maybe just feeding it smaller inputs helps it focus on finding like the important information first in like just a short sequence, and then it has an easier time expanding to longer ones. Yeah, since writing this paper, we've also tried running these methods on even bigger models, like 1.5 billion parameter transformers. And these results don't transfer 100% to much bigger models, but it seems like much bigger models also suffer from a lot of the problems that we saw here. And they also seem to benefit sometimes from shorter sequences. There's another question. How is position diffuse attention applied on later layers of the transformer? That's a great question because I didn't necessarily explain that. So let's go back to the slide because the answer is very easy. You just do the exact same thing in every layer of the transformer. You just use the attention in this way at every layer. So yeah, instead of adding position embeddings at the bottom of the transformer stack, you just add them at every layer.
Hi, if I may
Yeah.
add a comment to this. So my confusion was regarding that the value array would change for the later layers, right? Because that is based on what the self-attention did in the previous layer. So how would the caching work exactly?
I'm not sure I understand your question.
So so initially you have the value array, which is the initial token embeddings.
Yep.
Coming from the embedding matrix. So at that part, there is no problem, but later the value array also depends on how the self-attention combined the value array of the previous layer.
Right.
Right. So if the key and query are changing in previous layer, then the value array is also changing in the later layer. So the caching won't work, right?
Why won't it work?
No,
So
so
I think that if I may try to clarify, because I'm also think this. So the value, for example, at layer 1 or 2 is affected by the key and query in layer 1, and then if you are, I guess that, so maybe it depends on what you save, what you cache exactly, but in the final layer, it is affected by the position embedding of the previous layers.
In the PIA model,
What's the PIA model?
the position fused attention, like in our
Yeah.
model.
Mhm.
So you're saying that the values are affected by the keys and the queries.
Right.
So sure, but the problem with so in the typical transformer, right, when you input your words, every word, like if my sentence is the cat's out on the mat, when I'm inputting that into the transformer, I'm not really inputting that. I'm inputting the at position 1, cat at position 2, right? So you're not inputting cat, you're inputting cat plus 2. And throughout the layers, even though we kind of mix these representations and we kind of combine them together, the transformer somehow assigns some kind of positioning value to every output. And it's somehow in each of its outputs, it represents a position of each word. And that's why you can't do this kind of caching where you change the positioning information, because it's just, you have this, vector of size 1,000 and it has lots of numbers, but you don't know which of those numbers are positioning related, which one of those are, content related. In our model, the words that we input are just words, and our outputs are just combinations of words that have no positioning information. Sure, there's positioning information in the keys and queries, but that never gets to the outputs because the outputs are just weighted sums of this, right? And so that's why we can cache and reuse representations, because our outputs never have any kind of positioning information that would prohibit them from being reused.
Yeah, but so you mentioned that this is the output is the weighted sum of the value information.
Correct. Yeah.
Right. So this weight, so in that, so we have the weight that are coming in from these keys and queries, right? So the way it is get combined, that depends on the positions, right?
Okay, yeah, you're right that the weights have some positional knowledge, but the outputs don't really contain that because they're just a weighted sum of the inputs. I think I understand what you're saying, and I guess my the plain answer is that this works, right? I just empirically ran this on a bunch of different data sets, and it works really well. And if you do this with a normal transformer, it won't work. So the answer is that empirically it works. And neural networks aren't super interpretable, so I can't know exactly why it works. But my intuition is that our method works because it doesn't have any explicit positioning information in the outputs. You're right that the outputs are affected by positioning information, but they don't like implicitly contain or explicitly contain.
Okay. Yeah, sure. So I guess like just one final question then.
Yeah, for sure.
During implementation, how does this affect our forward pipeline? So once you have the cached representations, that is only for the final layer of say D4, D5 and D6, D4, E5 and F6. And you are just recombining them with respect to these new positions, that is D1, F2 and E2 and F3.
Okay. Are you talking about this?
Yeah. So like when you are caching from here, D4, E5 and F6, how is that getting reused in the next stage?
Oh, sure. Yeah. So you can see this in the code, but we just, we save these in memory. And then, so usually in the code, you have key queries and values are equal to the input. But if you want to use a cache, your queries are the same, but your keys and values are input concatenated to memory.
Okay.
Yeah.
Sure. Okay. Thanks. Thanks.
Oh, okay. We have one more question. Can we extend two-state training to three-state training? Yeah, good question. I ran like this random search where I looked at 3, 4, 5 stages with lots of different hyperparam settings, and it never actually improved performance. So yeah, it's a good idea, but it doesn't actually improve performance over two-state training. So two-state training is super simple, and it also works the best.
Do you have any intuitions as to why attention fails at longer sequences? What's going wrong there?
Yeah, I don't know. We need to figure this out. I mean, looking at longer sequences is just so much harder than looking at shorter ones. I guess also in lots of our data sets, there aren't a lot of long-term dependencies. Even when you're reading Wikipedia, which has really long articles. So most documents on the internet are like 500 tokens long. They're very short. And we're definitely not going to learn any long-term dependencies there. But even when you're reading Wikipedia, which should have some, long-term dependencies, it's still not something that happens very frequently. Most language modeling happens in like the last 100 or 200 words, maybe even less. And so I guess it might also be the fact that it's just such a rare occurrence in the training set that the language model doesn't really want to spend effort.
Gotcha.
Final questions?
Well, there's one question on Zoe. Do you think your newly proposed approach will have a positive impact on representation done by encoder-only conformer like BERT? They will work better for transfer learning?
Oh, do I think which approach will have a better outcome for BERT?
Your approach.
Oh, I mean, so stage training is already used on BERT. So the answer there is yes, I guess, because it already is. But it's not my approach. It's just something we analyzed in this paper. I guess maybe you're talking about position-infused attention. Caching probably won't help BERT too much because BERT is usually applied to very, very short sequences. I know from the Roberta authors that when they were building Roberta, they tried building like a version of Roberta that looks at 1,000 or 2,000 tokens, and that didn't actually improve performance. So because a lot of the tasks that BERT is applied to are on very short sequences, sometimes only a sentence long, caching isn't really going to help there. Longer sequences are more of like a language modeling GPT-3 type of thing.
Okay, cool. So thank you very much for the interesting talk.
Thank you for the great questions. I hope you guys found this interesting. Thanks for coming.
Yeah, bye. Yeah, bye everyone.
Thanks everyone. Thanks for hosting, Yanai.
Thanks. Bye-bye.